Stavros Christopoulos, Associate Professor of Physics at Sorbonne University, Abu Dhabi. The second presentation will be from Dr. Joumana Rifai, Assistant Professor of Physics as well at Sorbonne University, Abu Dhabi. And we will end the presentation with a presentation from Dr. Samuel Fang, Assistant Professor of Mathematics at Sorbonne University, Abu Dhabi as well. Because we don't have a lot of time, the session will be 45 minutes. They are happy to take any questions just after the session, maybe inside here, or we can have a small space for you to ask any questions. So please, Dr. Stavros, if you would like to start. Thank you.
Hello, everyone. Hope you can hear me. Hope you're comfortable and not too hot. I'm going to begin this session with a research project which I am leading and which is entitled Nanocomposite Optical Films. The idea here is to create optical materials that will create energy-solving solutions, basically, energy-saving solutions, while at the same time, hopefully, being on the biodegradable side. So I don't know the expertise of the audience, so allow me some introductory remarks so everybody can follow up. So composite materials in general are materials that are having at least two different compounds in them, and there have been there in human history with numerous examples. Other of them can be artificially generated or fabricated. Other of them are naturally occurring. It is much less heavy and much less brittle than glass. Finally, an example of a naturally occurring material is simply wood and plants. You have long fibers of cellulose, which are stuck together with a weak adhesive, which is naturally occurring as well, and it's called lignin. This formation gives the ability to plants to grow taller and to have some certain flexibility. Now, generally, scientists are very much inclined, the last couple of decades at least, to create composite materials that are using nanoparticles in them. And there are several reasons for this. I thought I should list at least 3 of them. So as we see over here, nanoparticles, due to the nanoscale of their dimensions, they can improve in an enormous amount the homogeneity. We have 3 solutions here, each of which has a different size of particles as a solute in them. And as you can see, the one with the bigger particles over here will have regions where the particles cover more or much less of a particular area. That means the properties of the solution vary enormously from one point to the other. As we reduce significantly the size of particles that are solved inside the solution, and we go to the nanoscale, then we basically, if we let them float and disperse nicely throughout the entire solution, then all the areas look pretty much similar. That means they will carry the same type of properties in the entire body of the solution, making the solution homogeneous. The second reason is that nanoparticles increase the interaction surface at a very large scale. The interaction surface is basically, when you use an active material, all the phenomena that you're going to actually observe, they appear most of the times on a particular surface of that active material. So the bigger surface you have, the better that is. Now, if you have a certain amount of active substance and you start chopping it down, you are essentially creating more and more surface, which means if you go to the very small region of nanoparticles, in the nanoscale region, you have effectively created a huge amount of interaction surface, which means that you have created a material which is much more efficient with a much smaller initial substance. Finally, in grace of their extremely small size, of their nanoscale size, nanoparticles can give birth to exotic phenomena, which are quantum effects. In a very random, again, example there, the number is extremely big. In a very random example, the vial on the right hosts big gold particles, which we are all familiar to the way they look like. But if I reduce the size of the gold particles significantly to around 100 nanometers and even down to 20, the solution starts looking purple or even red. And that is based on the properties that are giving birth through the nanoparticles. So what we're going to do today, to show you the research that we're looking at, is we're mixing 2 basic things. The one is a polymer matrix, which is low-density polyethylene in our case. It's for a proof of principle mainly. And in that, we're going to embed nanoparticles of different types and sizes. The nanoparticles initially come to a form which is shown over here in a powder form. So just indicatively, so you understand what we're working with, we have zinc oxide, silica, titania, alumina as unary suspensions, but we also have heterogeneous combinations, which you can see over here, Ti-Si, alumina-Si, and so on and so forth. Again, in different sizes also, to check how the properties range according to the size of the particles. So, there is a multi-step fabrication process. I'm going to get through it slowly so we can all understand how we can produce them. So we receive the powders, and the first thing we do is pass them through a milling process. That is basically hardened metallic balls that mechanically, what they do, they mechanically de-agglomerate the initial powder. It's not our purpose here to make the size of the particles smaller, it's just to de-agglomerate them. At the same time, we have the opportunity to add the dispersant, which in this case is polyacrylic acid, and that's an agent which will help us a lot in the homogeneity of the final product. So what we do afterwards is pass them through a simple wet sieving process, which is effectively there to remove the biggest of the agglomerates that we have created. The twist that we add in the fabrication process here is the third step, which is called freeze granulation. So we get these wet sieved suspensions that we have created, and what we do is inject them with liquid nitrogen. So we freeze them and we create like big chunks of agglomerates of nanoparticles. But the most important thing is that they are extremely brittle now because they have been frozen at a state that is pretty much unstable. So having taken them from the wet sieving process, they might include some water. And you wish to remove that to improve your homogeneity. So what you do is pass them through a freeze drying process in which what you do is that you regulate temperature and pressure in order to remove water molecules through sublimation. Then the slurries, they look basically somehow like this. These are SEM images of the frozen granules for 3 different suspensions. This is, I know you cannot see actually, so it's alumina silica, titania silica, and alumina titania. The last part is the mixing. We do that through the blending process, which happens through an extrusion fabrication technique. So what do we do here? We take the polymeric matrix. It comes in pellets most of the times, and what we do is we mix it with the granules that we have already created. So the process looks schematically like this. The yellow part here is the polymer, and the big chunk of matter over here, the granule, that is comprised of different types of nanoparticles, is in the middle. So first we start by increasing the temperature in order to increase the mobility of the polymeric chains, so it can be mixed easier. And then we advance the pressure, we increase it in order to break that granule down to much, much smaller bits until eventually all the nanoparticles that were contained in the granule are freed to move and disperse throughout the entire body of the matrix. And this is how we obtain what we believe is a homogeneous material at the end of the day. So to help you visualize the process a little bit, I found an animation from a company called Muraplast, which is actually will help you see the whole process in a much more direct manner. If you follow me here, the white dots is the polymer, whereas the dark dots are the granules that we have prepared through the process I've shown you before. So what happens in this case is that we feed all the particles inside an extruding device. Inside this extruder, temperature rises, pressure rises, so the mixture, the particles are made to mix very well together, and the granules are breaking down to smaller bits. The entire material will pass through a ring-shaped opening, creating a polymeric tube, whereas in the middle, over here, there's a constant flow of air, which, according to what its intensity is, it will define the thickness of the material. Then cylinders at the top of the extrusion tower will create the flat, familiar shape that films should have. And that's the end of the process after extrusion. So, after we prepare the films, what do? Introductory measurements would mean that we need to check elemental composition, crystallinity, dispersion. These are the basic characteristics of the material as there should be at the beginning. So, a simple X-ray diffraction graph here shows you that if we have particular positions for these peaks, we can identify the elements that are present in the final material. Moreover, it is the sharpness of these peaks, whether they are more round like this or where they're more sharp, that allows us an initial estimation of what is actually the particle size in the final material. If you follow me to these measurements here, this is simply how the film looks like in an SEM image, but in images D and E, we are basically conducting energy dispersive X-ray measurements. So the black or the more dark background, I'm not sure how you can see it over here, the darker background in both cases is the polymeric matrix. The lighted spots, are they obvious or not? I'm not sure if you can see some small spots inside here. The small spots verify the position of particular elements, not only their position, but also their size. So this is the position that you can find titanium cores, and this is the position where you can find aluminum cores. So they all seem to be of relatively the same size, but more importantly, they are all dispersed very evenly throughout the entire polymeric matrix without creating agglomerates and without being concentrated, isolated in certain places. This is actually coming from the titania alumina sample, which means all of these images are the same material by looking at different thing every time. So we are humans, or at least we claim to be, and we are looking for applications that have to do close to the visible part of the spectrum where we can actually see. So that expands between 400 and 750 nanometers, as it is well known. For wavelengths that are below that, we have the ultraviolet region, which generally tends to harm living organisms. It's not, let's say, very pleasant for them. So up we go to longer, much longer wavelengths. We extend to the infrared part of light, which, for our purposes at least, we will connect it only to heating effects. They create mechanisms that produce heat, thermal energy. So the first thing we need to do here, when we take our films, is optically characterize them. In this graph, I have the transmission and the wavelength to see how much light is passing through the film according to the wavelength of the radiated light. So, as you can see, the net LDPE film, which means it's only the polymer, we have not included any of the nanoparticles, allows a huge amount of radiation to propagate through it. So you see, even in the UV region, the visible region, and the infrared region, all the light is allowed to pass through. Now, as we start adding nanoparticles, this curve shows if we add alumina, this curve shows if we add titania alumina, and the final one over here shows us a sample that only contains titania. You see that, first of all, gradually and effectively, we can completely remove the part of the spectrum which is close to the ultraviolet, while at the same time we are able to regulate the intensity that passes in the visible and in the infrared region. So that is a proof of principle that we can actually regulate which areas of light can pass through, can propagate through the films, and which cannot. By conducting some additional measurements of reflectance and applying some analysis which is based on the TAUC method, we're able to extract the energy band gap of these samples, which is fine. The idea is that we can connect that immediately to the particle size because of quantum confinement. So what we have established here is that the particles at the final product have the same size as the particles as it was received at the very beginning. This has been a kind of violent process that we have taken them through, and we would like to establish that indeed their sizes has not altered, at least the primary size of the particles. The idea here is that when you have some properties in mind, the particle size is what defines them. So if that changed, so would the properties. But here, we can start selecting properties of particular nanoparticles, knowing that our process will not alter their size until the very end product. So we have achieved a uniform dispersion of preselected unary and heterogeneous combinations of metal oxide nanoparticles in a polymer matrix, and that's the proof of principle. The bulk scale method that we're using is both cheap, efficient, and it can produce large quantities of samples. So it can be used either for everyday or for industrial uses. At the same time, it's the same method what is allowing us to tune the optical properties by just simply regulating amount, size, and type of the particles. This is a very high conventional method. It's been used for many years, so it is very well known. It's very well established, which means you can use it extremely easily. And in this way, we can customize the final material depending on the applications that we have in mind. And I'm going to bring some of them to your mind now. So, of course, you might think we can use this to create filters, we can create covers for lenses, and we can, of course, create covers or coatings for flat displays, which can use as anti-glaring or anti-reflection, depending the part of the radiation you want to avoid. But I would like to draw your attention to one particular application, which is basically to create covers for greenhouses. That's one of the things. Apart from buildings and glasses and so on, you can create covers for greenhouses. So a plant, and it's a particular type of radiation, which is called photosynthesizing active radiation, in order to grow, to photosynthesize. This part matches very well with the visible part of the spectrum that I've discussed before. Now, it changes according to the variety of the plant, but it's almost the same all the time, which means a plant would need all the visible it could get, avoid completely the ultraviolet part, and the infrared, which introduces heating effects, would depend from country to country. I'm very excited to say that we're on the brink of creating a pilot program with a local UAE company, a farming company, in which we were going to cover their greenhouses with the material that we're using, in which case all the visible passes in, which is important for the plants to grow. UV is completely absorbed, while obviously the infrared part is completely reflected. In this way, the plants have the initial energy that they need in order to grow, but at the same time, we're avoiding all these extra heating effects that would create energy, that would lead to extra energy consumption in order to cool that structure down, because here we have to cool the structure down for the plants to have the optimal temperature to actually grow up. So future directions include study of the dispersion and particle statistics. Apart from the optical properties that are very important for the actual application, we should go through characterizing electrical, thermal, and mechanical properties while exploring extra nanoparticle combinations. The most important fact, though, here is the fact that because this method is an extremely conventional, well-established method, we can completely replace LDPE, which, let's face it, it's not the most environmentally friendly material, and it was used only for a proof of principle, with much more environmentally friendly and biodegradable materials, because they are all polymeric pellets, which you can use in precisely the same way that I've shown before, like polylactic acid, polycaprolactone, polyglycolic acid, and polyhydroxybutyrate. So this research effort has been achieved through the collaboration of several institutions, the number of which is actually growing steadily because of the promising results that we have already had. At this point, I would like to thank you for your attention, and I will hand over the floor to my colleague, Dr. Jouman Al-Rifai. Thank you very much.
Good morning, everyone. Pleasure to be here. In the second part of the series of presentations, I will be presenting to you our current research related to fabrication and characterization of nanostructured layers for energy harvesting applications. This work was made possible through the Sorbonne Abu Dhabi Research Fund that we applied for at the beginning of 2022. All the sample characterization was completed at Sorbonne Abu Dhabi, and with help of the members of the Science and Engineering Department, with a collaboration with Griman Laboratory in France. In terms of our particular applications, we're looking to fabricate and characterize nanostructured layers for applications in energy harvesting. Energy harvesting can be divided into four important types: solar energy harvesting, thermoelectric, piezoelectric, and radio waves. In all these four applications, the important process is to capture small amounts of energy from the immediate environment of a device and convert that collected energy into a usable power to allow the device to generate its own power supply. For our particular case, we're interested in incorporating both solar energy harvesting and thermoelectric energy harvesting into one layer. We believe this will enhance the performance of harvesting and at the same time allow us to incorporate more than one technique, mainly because solar energy in itself would generate a large amount of heat, which is what is necessary for thermoelectric energy harvesting. If we don't use that heat, it will just completely go to waste. As opposed to large-scale solar and wind installations that generate large amounts of energy, harvesters provide only a small amount of energy or power needed to drive low-energy day-to-day electronics. So again, all day-to-day devices would be able to generate their own necessary power supply. This leads to a number of advantages and possible applications. If energy harvesting is applied properly and with sufficient research, power cords, batteries, exchanging batteries will become unnecessary. And the idea is that in one day, devices would require minimum maintenance and therefore become independent of any physical interventions. This becomes very useful if you have devices that are installed in remote or hard-to-reach locations. Two important applications of harvesters will be in self-powered wireless networks, wireless sensor networks, and applications in IMEs, which are implantable medical electronics, where currently the cost of exchanging batteries, the battery capacity, the size of the battery, and not to mention the large environmental footprint that comes from all of the discarded batteries after use is a challenge. And especially in IMEs, recent research has been reported on using harvesting applications for such devices. But if we want to look at the overall picture, we have to also consider some of the challenges and limitations of the harvesting technology as it exists at the moment. Harvesters produce a very weak and unstable power. So currently, only devices that require a small amount of power can be connected to harvesters. We also have to count for any sudden shutdowns in the harvesting device and therefore any sudden shutdowns of the main device itself. Another important factor here, another important limitation is that if the device that you have connected to the harvesting device, the energy harvesting device, is costly to manufacture and costly to install, then your harvesting capacity needs to be large enough to match the cost of your device. So overall, high efficiency, high output, and low cost harvesters are necessary. Harvesting technology is necessary. This is where nanostructured layers and nanoparticles in general can play a role, because it has been shown in several research works that nanostructured layers and nanoparticles incorporating these materials with the existing technology, harvesting technology, can improve solar performance. So an improved solar performance here would mean that you have enhanced the absorption of light. So you can absorb more light and therefore generate more energy from the absorbed light. The other improvement that is expected here is that there should be an improvement also in the thermoelectric behavior of a material. And I haven't defined it yet, but what we mean by thermoelectric harvesting implies a coefficient called the Seebeck effect. And this is basically a phenomenon where you would subject a semiconductor or a conductor to a variation in temperature, and that variation in temperature would generate a small electric current. So improvement in thermoelectric behavior implies a larger electric current out of your device with a smaller temperature variation. And even though we're not considering any radio wave energy harvesting for our particular application, but it's important to state that future research involving radio wave harvesting solely relies on nanomaterials. The variations when it comes to the nanomaterials and the nanostructured layers depends on the, so from one research group to another, depends on the material selection, and it also depends on the fabrication process of this material. For our particular application, we are considering silicon and silicon germanium nanostructured layers. And if we look at some of the fabrication techniques when it comes to silicon and silicon germanium, research groups have already looked at fabricating nanostructured silicon germanium from thermoelectric performance using what is known as a metal-induced crystallization with aluminum interlayers. This means that during your fabrication process, the deposition process of the material, you incorporate aluminum into your process, and then you subject that material to a high temperature process in order to activate the metal-induced crystallization. This, as a process in itself, as a fabrication process, requires a large amount of heat, and it also requires a lot of time. So if you're using any materials in your layer that are sensitive to high temperatures, you have to eliminate those completely. So you're running into some restrictions when it comes to your material choices here, and you're also going to have to consider the time aspect of this. Regardless of this minor disadvantage, Seebeck coefficient in the range of around 150 microvolt per Kelvin can be generated from such a fabrication method. In general, for silicon germanium, your thermoelectric performance can be as high as 250 microvolt per Kelvin. As we are also interested in the optical performance of our device, we can look at another fabrication technique by another research group concerning fabricating nanostructured silicon. And you'll see that what they use here is an electrochemical etch of silicon to generate porous silicon. So you see at the top image here is the silicon layer with nanostructuring on the surface. It's no longer a smooth layer. And this is a cross-section microscope image that you see the nanostructuring as the depth of the layer progresses downwards. And this has already shown an improvement when it comes to the reflectance. So as it is subjected to optical light, your reflectance from the pure silicon substrate will drop if you have nanostructuring on the layer. You can also incorporate silver nanoparticles in the process, which will further enhance the enhance absorption. Lowering reflectance will automatically imply that you have enhanced the absorption of your material. Even though it's a successful process when it comes to lowering the reflectance, the one disadvantage of this is that you start with a crystalline silicon wafer, which is not a cheap material to start with in the first place. And you electrochemically etch that material, which means you're eating away in the surface of that layer. So you're generating material waste as well. So you start with an expensive layer, and you eat it away to generate the porous layer. So what we are suggesting for our particular fabrication process, for both silicon and silicon germanium, both of these materials would work with our process, is to use an excimer laser annealing of the material. So we use a excimer laser, which generates a fixed wavelength of 248 nanometers. So you're in the ultraviolet range. The laser is then connected to an attenuator, which allows you to control the energy of the pulse generated, and you can generate a single pulse or multiple pulses for that laser. Then you have a number of optical components, which I will not go into the detail of. And then finally, you have a projection lens that projects the laser pulse onto the sample stage where you would place your silicon or silicon germanium material. And you start with an amorphous silicon or an amorphous silicon germanium material, which means it doesn't really generate, or it doesn't really conduct electricity at that point. And the fabrication process for an amorphous silicon or amorphous silicon germanium can be as high as 10 minutes. So it's actually a very fast fabrication process. The laser pulse, if it's a single pulse, you're talking about 1 second, basically. So the whole entire process is not time-consuming. What happens, though, as the laser shines onto your amorphous silicon or silicon germanium sample is that it will absorb part of that light or that energy as heat. It will create a solid-liquid interface, and that interface or that top layer will propagate into the depth of the material. How far it propagates downwards depends on your laser energy. The higher the laser energy, the more the melt depth is going to be. And then the sample cools down and the heat dissipates, and the solid-liquid interface will move to the center and then back at the very top. And what you're left with is a polycrystalline material. So at this point, your material can actually conduct electricity if need be. It's important to note here that only the top layer of your pulse, if I go back one slide, only the top layer of your material is subjected to the laser pulse. So in terms of a thermal budget, this is a low thermal budget process. So any underlayers that you have underneath will not be subjected to the laser pulse and will not be heated. Nevertheless, laser annealing is a harsh fabrication process, and we expect surface roughness to occur due to that laser pulse. And you can control that amount of surface roughness. So the image here that's labeled A on the left shows you a very smooth laser annealing process where you don't have a lot of surface roughness at the top. However, if you increase the energy of that laser pulse, then you generate a larger amount of surface roughness on the surface. The other way to control the surface roughness is through the use of single pulse or multiple pulse. This image here shows you the single pulse treatment, which has a surface roughness but is not as high. And you will see here in the lower image, the multiple pulse treatment, in that case, generates a large surface roughness. Now, surface roughness is not necessarily something that a lot of applications would like. However, for our particular application, this is quite efficient because you can control the amount of surface roughness, and therefore you can nanostructure your layer using the simple laser pulse. I'm going to skip that slide and go to the results. Since this project at the moment is currently under publication, I cannot share a lot of the details when it comes to the parameters. However, I can share with you some of our optimum results. We have measured the samples using a UV visible infrared spectrophotometer to analyze its absorption of light over a large scale of wavelengths. And we see an absorption enhancement of a factor of 20 to 25 at 750 nanometers and 1,100 nanometers. So it has improved, and it can be tracked to the laser pulse itself or to laser treatment, can improve the absorption of your initial layer. We also conducted some resistivity measurements for our samples. And resistivity measurements are conducted using a 4-point probe, which I have an image for here just as a schematic. You use 4 probes, you bring them in contact with your layer, you pass current through the outer 2 probes, and you measure voltage through the inner 2 probes. And from that, you can calculate the sheet resistivity of your material. And the optimum resistivity values for our case for a single pulse laser treatment is around 0.3 milliohm centimeter. This is just merely an indication that you have a conductive layer. So instead of the amorphous layer that you started with, now you have a polycrystalline layer. We also confirmed the change from amorphous to polycrystallinity using a Raman spectroscopy as well. In terms of thermoelectric behavior, Seebeck coefficient measurements that were conducted show values of around 300 microvolts per Kelvin at temperatures of 400 degrees Celsius. So in terms of recent research, these values surpass the reported values. So finally, to sum up, energy harvesting technologies, research in energy harvesting technologies needs to progress because as a source of energy, it is renewable and it is abundant. We have, or generally research using nanostructured layers have shown to improve the behavior of energy harvesters. And in our particular research, we've shown a low-cost nanostructured layer suitable for energy harvesting applications fabricated from polysilicon and polysilicon germanium, which are materials that are frequently used. It's not an exotic material. Applications can involve using these layers on flexible substrates because your temperature budget is low. That means you can put them on any cheap material. You do not have restrictions in terms of a thermal budget. Finally, the thermal budget of the fabrication process will therefore increase the integration flexibility, lower the production time, and lower the cost of your fabricated device. And I thank you for your attention. Now I leave the floor over to Dr. Samuel Feng, who will discuss his work.
Hello, everybody. So today, I want to tell you all a story that started the first day that I landed in this country in mid-August 2014 in Abu Dhabi. I met these two guys, Dr. Omar El-Dakkak and Dr. Bashar Zahawi, and we became friends. Dr. Bashar is a power engineer. Dr. Omar El-Dakkak is a pure statistician, mathematician. I'm also a mathematician. And over time, our team grew, but basically grew because, like with all good friends, you talk and talk, and you realize that you have something more and more in common. And we discovered that there's actually a really cool math problem that sits in the way that we develop our power systems for incorporating renewable energy. And this is a common problem that I think a lot of us are aware of. If we want to incorporate renewable energy resources, so think, for example, solar or wind, one of the things that makes them a little bit more difficult is their stochastic nature, right? That means that it's hard to predict because it's tied to weather or it's tied to something else, uncontrollable. It's hard to predict exactly how much harvestable energy will exist at a particular place at a particular time, right? And so that's why I'm using the word stochastic or random. There are lots of different words we could use to describe this difficulty, right? And in the entire process, right, there's a lot that happens in going from a solar panel to energy in your home. There's a lot that happens there. But along the way, along this entire power systems planning journey, there exists a specific problem that's going to be the focus of the next 15 minutes I have with you. And that's what we call the density estimation problem. It's a common statistical problem if there are any statisticians in the room today. But it's the density estimation problem. And I want us to focus really, really well. If you're with me on this next slide, you're going to be good for the next 10 minutes, okay? So the density estimation problem, what I want you to imagine is you have maybe some sort of instrument that's collecting and measuring solar irradiance, say, for a day, right? So you have something that's measuring and accumulating, and it's giving you a number of like, oh, we had this much sun available on a particular day. Well, like any data, at some point, what you collect is you collect a pile of numbers, right? You collect a pile of numbers. And with any pile of numbers, nobody just stares at this. Sometimes movies will dramatize people just staring at a pile of numbers, but no one actually works like that, right? Instead, probably the first thing you would do with a pile of numbers is you try to visualize it. And so you would probably do something like this in Excel. It's called a histogram, right? Histogram is what happens when you take a number, and then you create some buckets. So here, it's hard to see, but I've got different buckets. So for example, right over here, I have a bucket corresponding to the 400 range. This is just some data concerning in Germany, wind and solar power production, right? And one of these stochastic things. And then the height of this bucket corresponds to the number of observations I had from my data in that range. So this 400 bar is 70 high, and that corresponds to there are 70 days in this data set for which the production was between 400 and 499.999. Okay, so everyone's with me? Everyone's with me. Everyone's familiar with this very, very standard visualization of data. But I want to do something a little bit different because we need to find this idea of a probability density function, okay? Instead, I'm going to take all of my numbers, and it's hard to see, but for every number here, what instead I want to do is put one little vertical tick. So you see these little hash marks. Ignore this for now, but these little vertical hash marks right here, for every number here, I put a vertical hash mark on this horizontal axis. And once I do that, we start to notice a slightly different type of pattern. We notice that, okay, there's a little bit more black in the inside right here, right? And there's a little bit less, although I still have some data at this really low area and some other data at this really high area, right? And what's going on is that's representing, or that's our first notion of this idea of a density or probability density function. And that's what we have to actually discover in this density estimation problem. In other words, there is an unknown function which is resembled by this, I don't know if you can see this purple-gray, faint purple-gray curve right here. It's not the blue one, it's not the green, not the red, but there's a very faint purple kind of bell curve in the background here. Basically, in nature, there's something like that that exists that we don't know. That's the unknown that we're trying to discover. In short, the density estimation problem is to say, we want to know what is the density, by the way, sorry, the density, what that means is the values of this function, this mathematical function, correspond to the likelihood of generating data in that region. In other words, because we're more dense here, That's why we have a higher value in the middle here. And then we have lower values towards the side, and that corresponds to it being less likely, but not impossible, of generating data at the extremes. And that's captured entirely in this one mathematical function called the probability density function. Now, the difficult thing is we don't know that. We don't know the ground truth. We don't know what is the probability density function for a particular site and the amount of solar irradiance being generated. And that's the problem. Imagine we don't know the purple curve. We get a pile of numbers, and we need to reconstruct the purple gray curve. Okay, that's the density estimation problem that needs to be solved at a couple of different points during this power systems planning process. Okay? And it's especially challenging because of the stochastic nature of the resources we hope to deploy. All right? So so if I take this pile of numbers and I do a bunch of fancy math and blah, 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 I'll come up with an estimate. And that'll be something like the blue line, the solid blue line here. But if I were to take the same pile of numbers and give it to one of my collaborators, he can come up with a different estimate, like maybe this red squiggly line. And remember, we don't know ground truth in this problem. Right? We don't know who's right and wrong. So who's to say that I'm right or my colleague is right? We settle with a fist fight or what? No. So instead, what's been developed is a lot of different estimates for how we compare the quality of estimates, given, again, that we don't know ground truth. Right? We don't know ground truth. And so there's a bunch of like theoretical stuff, mathematical stuff that people like me love, but it's not for today. And then there's also more popular, growing in popularity are these what I'm calling empirical or data-driven estimates, where basically you try to compare the quality of different competing estimates by using historical data. It's a very simple idea. Okay? So you have to do this very, very carefully, very smartly as well. If anybody in the audience is familiar with like AI methods and machine learning, right? You're very familiar with the idea of validation and training and things like this, okay? So we've got a lot of different ways of comparing whose estimate's better than somebody else. Again, because we don't know the real answer. So we have to do our next best thing of just compare with each other. All right, so now I want to give you just four conclusions. I just have 4 slides that we're going to walk through together about what we've done in this specific statistical problem. All right? The first one is to say that classical statistics, which are called parametric models, they actually do a really bad job, especially with renewable energy resources. They do a bad job of capturing the stochasticity there. So what I mean by parametric models is these are older statistical models that assume a specific functional form. So any students in the room probably get a little terrorized at seeing stuff like this. This is an exponential, a square root, blah, 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 right? But basically, these were developed 70, 80 years ago, and they assume a specific functional form. There's a formula. There's a math formula here, right? But if that formula is wrong, you end up producing a lot of error. And that's what we found. So for example, we took a bunch of sites in in the UK, Northern Europe, take a look at their wind speed data, formulate a histogram, so that's what's down here. And if you run the parametric model fits, they don't fit the data very well. So this is just an illustration. Of course, you have to be a little bit more quantitative. You don't get to just produce a plot. But this is to summarize the fact that the parametric models don't do a good job of capturing the stochasticity that we observe in this slide, at least with wind data. Everyone with me, hopefully? Good. All right. They're not doing nothing, but we can see that they're making their hump in a slightly different place compared to the data. And again, the data is the histogram that I have over here. So the bars over here, that's the raw data. And then the curves, the lines here, are supposed to be really, really close to that, but they're not. Okay? And so, we spent a lot of time in school learning a bunch of math. Not all of us, but basically, after parametric models, there's this stuff called non-parametric models, right? We're terrible at giving names to things. And non-parametric models basically say, well, let's relax. Let's get rid of that assumption that there's this specific way of writing the functional form of this unknown probability density function. Instead, let's use the data to build and customize a specific type of function for this data, right? So hopefully this will do a lot better. So kernel density estimation, KDE, is the most common method of trying this for the first time. And we took the same data. We developed a kind of a flow chart. This is actually not that complicated. It's just you have to have a sequence of steps that you can follow to develop an algorithm to carry out a bunch of steps. And it does a lot better. So that's evidenced by, so this is what we had on the previous slide. And now we're really, really close to those bars using a kernel density estimate. Now we discovered something that was interesting. When you do kernel density estimation, there's a particular technical parameter called a bandwidth. And in a lot of other applications, people do KDE. People do this density estimation in other fields outside of renewable energy. And very often the bandwidth's not important. But we discovered that tuning this bandwidth parameter is extremely important, at least when estimating wind and solar. If you tune it properly, we were able to harvest or do about over 90% better than the currently used default methods, parametric methods that are employed in various sites around the world right now. So it's a pretty big improvement in the accuracy of estimating, at least on this slide, what I'm showing you right now, at least in estimating the stochasticity of wind speeds. Well, all right, so that makes us feel pretty good about ourselves, and we then say, okay, let's do the same thing with solar, all right? We did the same thing with solar, and it was worse than the parametric model, all right? But then we said, okay, no, let's figure out why. And the reason has to do with the fact that with solar, there's a different nature to stochasticity. It's much more common for solar energy to be completely off. It's called night, right? So, or even during the day, it's called a cloud, right? So this actually exposed a mathematical weakness in kernel density estimation that's kind of technical, I'm not going to get into. But we adapted, therefore, a different non-parametric method, which we called RTLLR, root transform local linear regression, adapting a pretty modern method created by these really, really good statisticians, I think in 2013 or 14. It's pretty recent, right? It's math created in the past 10 years. And we showed that, all right, if you take a bunch of sites in the southwestern United States, solar sites, we can rework all the math to just be a simple sequence of steps to follow. You don't have to understand the math, just follow these steps. And we find that we do pretty well again. So the black lines on these plots are going to be the beta distribution, which is the parametric model that's the standard for use with solar. And what you'll see first of all is if you can see the red or green, this wavy that starts down here, that's the kernel density estimate from the previous slide. And it does worse, and it does worse very specifically at this low region around zero output. Notice how these are coming down, whereas the bars down here are really, really high, okay? And so what RTLR, what this method does is it corrects for that, and it does significantly better. So in this situation, our proposed method was able to decrease the error by 30–40% compared to the beta distribution, where even the KDE from the previous slide was actually doing worse, doing about 10–20% worse than the beta distribution. So it's not just a completely simple story of just use one thing, use one hammer for wind, and then use it for all the other problems that you might have. You have to adapt your methods for the applications. Okay. And then finally, I had this really, really awesome student. I was hoping he would come today. He said, well, doctor, why don't we try doing the same thing but with household electricity consumption? Right? The amount of power that your home uses is also stochastic. It also varies because of similar reasons to wind and solar, right? Night and day, seasons, all sorts of effects. And so he did that. He said, okay, well, let's just try to estimate a household electric load, and he did an amazing job. He developed a graphical user interface to kind of do a lot of this analysis that I've been showing you automatically in a very user-friendly way. He developed a scoring system, so now you can just score different methods. So we're just comparing various methods here, and it turns out that this RTLLR method also did really, really well on at least a bunch of different residential and enterprise sites in the UK. So that's my 4 stories, right? Parametric model's bad, kernel density estimation pretty good, non-parametric model's good, got to be careful with solar, and we might be able to use the same thing to estimate electric load, okay? Now, moving forward, there are kind of 2 big unresolved questions in my mind. The first is a little bit tricky because of the political side of it, but we need to understand the cost of our previous mistakes, right? What I've told you today, hopefully, I can at least convince some of you that there's a better way to do this specific type of density estimation, but how much better does it improve the bottom line of a particular power station, for example? Or what's the penalty of not moving, right? Because this has only been implemented in a very few, our technology has only been implemented in relatively few sites, right? And so that's a question that, again, mistakes get made, but we really need to characterize this loss due to not using what we have discovered is kind of the best way to approach this. And the second thing is we found in a lot of our research that the specific method, right, we have all these different formulas, there's a lot of details going on. The specific method and the specific renewable energy resource or whatever changes depending on site, sometimes and location throughout the world. And really that's what needs to happen, is there needs to be this collaboration between industry, academia, cross-disciplinary. That's hopefully the big story that I've told you today, so that we can deploy our natural resources, deploy our renewable energy resources as efficiently as possible. So if there's anything that I want to leave with you today, it's this kind of marriage between academic research, industrial research. There's this marriage between mathematicians and statisticians and theorists with engineers. It's this marriage between power systems on the ground, delivering power to all of our homes, and the researchers like the three of us who are kind of working in a lab or in somewhere else. Let's keep it going. Let's keep those dialogues going, because that's how these ideas are going to be able to cross the boundaries that need to be crossed. So with that, thank you for your time. All of Dr. Stavros, Jumana, and myself welcome any questions. Please feel free to email us for anything or talk to us after the talk. And with that, I will hand the mic back to Manon.
Thank you all for your time and for your attention. We will continue our program today with another conference that is going to start in 5 minutes about damages to nature. So if you would like to stay, you're more than welcome to stay. Otherwise, if you would like to ask some questions to our three researchers, please feel free to ask your questions inside in the snacks area, as we don't have much time for Q&A. Thank you.
Dear guests, the event is now in session. Thank you.